Okay, in this lecture, we want to talk about the difference between single crystal materials and polycrystalline materials. So I want to go through first and just define what is a single crystal material. And all that is if we have a material sample that has some constant lattice structure throughout, so the lattice structure that we've talked about, whether it's BCC or FCC or HCP, if those just continue to repeat over and over and over again without break, without sort of hitting any boundaries or changing directions or anything like that, if that lattice structure persists throughout, we call that a single crystal because it's all part of a single lattice. Okay. And what I'm showing you here on this image, this is a image from a transmission electron microscope, and so you can see this is a scale bar of 3 nanometers, and this is for looking at silicon atoms, and you can see that the lattice that the silicon atoms are forming, and you can see that it's repeated throughout. So that's an example of a single crystal. Okay. So one thing to note about single crystals is that they're very difficult to fabricate. It requires extremely careful process control, things like clean rooms, vacuum deposition, which means that all of the air is evacuated out so that there's no possible way to contaminate the sample that you're creating. Okay? And the reason that we do all that is that single crystal growth, to get a single crystal, we require growth from a single nucleus, okay? Because otherwise, if we have multiple nuclei growing together, they won't necessarily form the same lattice, right? They're going to come together and form some kind of a boundary, and we'll talk about that in just a minute. Okay, how about properties of single crystals? So we've talked about FCC and BCC and HCP and kind of shown you some other structures as well. But in a single crystal, properties are typically what we call anisotropic. Hopefully you've heard this phrase before, but I'm going to remind you of it. What that means is that the property value is dependent on the direction that we measure. So here's an example to illustrate that. Let's think about the elastic modulus in BCC iron. Okay, so normally when you think of a piece of iron that you might get at the machine shop, you know that it doesn't really matter which direction you pull on that piece. It's going to have the same properties in all directions. But at the single crystal level, the modulus or the stiffness that you get by pulling on that single crystal, let's say along an edge direction. So in this case, pulling it along this, this would be your something like a 100 direction, pulling on it in that direction gives you one modulus of elasticity, in this case 125, whereas pulling on it in the diagonal of this BCC material is going to give you a modulus of 273. So significantly different modulus values depending on the direction that you pull. Now, if you remember what the modulus of iron actually is, you would typically report it as something in between there. And again, we'll talk about what that is. But the bottom line is that in a single crystal, usually properties are anisotropic, meaning that the direction that you're measuring them affects the property that you measure. Okay? One more thing I want to mention about single crystals is that sometimes a compound or an element can have more than one single crystal structure, rather, that it forms. And it's going to typically be something that happens at different temperatures, but not always. And when the fact that they have multiple structures is what we call polymorphism or allotropy. Okay, so classic example is iron, right? So again, this is going to be used throughout. Turns out that the polymorphism of iron is going to be one of the key features in a lot of our heat treating of steels, a lot of our choice of how we process steels in general, because we're trying to achieve particular properties that can only be achieved by us moving from one crystal structure to another. Okay, so let me give you a temperature line here. And in the iron system, there are 3 critical temperatures: 912 degrees C, 1394 degrees C, and 1538 degrees C. Below 912 degrees C, the iron system forms what's called alpha iron, and it's a body-centered cubic structure. That's the typical structure that we talk about for iron. At between 912 and 1394 degrees C, it forms the gamma phase, which is a face-centered cubic phase. And then above 1394, it goes back to body-centered cubic, okay? And then above 1538, we get to a liquid, right? And I'm not going into why these are important yet. I'm just telling you that they exist, okay? One thing that you're going to find is that we can put a lot more carbon into iron in the gamma phase than we can at the alpha phase. So one thing that we might want to do is load up a bunch of carbon in the gamma phase and then cool it to the alpha phase. And we'll talk about sort of what happens when we do all those kinds of things to control the microstructure of steel. Another classic example of a material that has multiple possible structures is carbon, right? And I think you probably know that. This is not an exhaustive list, but carbon can form graphene, which you may have heard of. It's kind of a hot new material right now because people are able to do things like dope it to get very high electrical conductivities. It kind of is like viewed as almost like a super material right now. Even though I'm somewhat skeptical of its long-term use. But nanotubes, also something that you probably heard of. They can form fullerenes, diamond. Maybe you have a diamond ring. That's carbon, obviously, but it's not in the same form as the lead in your pencil, which could be graphite, right? So those are 5 different structures that carbon can adopt. Those are all allotropes of carbon. Let me bring up one more, and that's tantalum. And the reason I bring that up is because this is one that I've personally worked on a lot. Back when I was doing my PhD at Cornell, my group was, one of the projects in my group was focused on looking at the phase transformation between tantalum from its normal BCC phase, which is alpha. So I'm showing you a BCC alpha tantalum. But when we were depositing it in thin film form, so that means that we would basically create we would buy a target of tantalum, we would hit it with plasma, we would sputter atoms onto a very, very clean surface and create very high quality very high quality films of tantalum on that. And when we would create them in that fashion, we would actually sometimes be able to create a different crystal structure, much more complex. In this case, we called it beta tantalum. And it's a complex tetragonal phase. Obviously, we're not going to talk about something this complex in this class, but the bottom line is that the allotropes exist all around us, and in many cases, they're critical for our engineering applications. And like I say, in this class, we're going to spend most of our time talking about how significant these allotropes are when it comes to processing the steels in the iron carbon system. Okay. So now I've told you a lot about single crystals. If you're racking your brain going, well, where do we ever use single crystals? There are a few applications, even though, as I said, they're kind of expensive to create, very difficult to create. So they have to be, you have to want to put them in there. The first, that's probably the most common, is in turbine blades or vanes for gas turbine engines. Okay, and the reason is because we get an enhanced creep resistance by using single crystal blades. We'll talk a little bit more about why that is later, and you'll learn a lot more about it in the class on the mechanical behavior of materials next semester in your studies. But basically, this is showing you this is the turbine vane right here, or turbine blade, and this is the surface. So you're looking at the structure here. So this is kind of a zoom in of what the actual surface is. You have a single crystal alloy, then there's some sort of a bond coat, and then you have a ceramic thermal barrier. Okay, the reason that the single crystal alloy works is because it prevents, as gas turbine engines run very hot, it prevents the long-term creep growth along that blade. Okay, and so what I'm showing you here came from a NASA plot showing you the year that was developed versus the temperature capability that was controlled by the creep life at 137 megapascals. Okay, so back in the 40s and 50s, our temperatures could run around up to, like, let's say 850 or something like that. And until we got to these red squares are just conventional casting blades. Then we moved to the green, which were directionally solidified. But then these blue curves, or these blue points, are single crystal blades, which you can see we've been making since the 1980s. But they give us a significant temperature enhancement over non-single crystal blades, purely as driven by creep. The other place that you are you've experienced single crystals is in silicon. The fact that you're watching this video on a computer means that you're using silicon single crystals in there. So single crystal silicon is used for semiconductors. It permits very high quality control over the doping and the electronic properties of that. So what these are actually, these are long billets of silicon, and then they're sectioned, they're cut into discs like you see here. And then those discs are processed in such a way using photolithography to create the transistors and things like that, and the circuit chips and whatnot that you see in your electronics today. So that's another common example of single crystal applications. And the final is less precision, but you may have used these. I come from a construction background, and so we certainly use diamond blades in construction. Those diamonds are single crystal, and they're embedded into the blade to give you exceptional hardness, right? So those are three common examples of single crystals that you'll see in kind of an application. Not the only ones, but certainly probably the most important. Okay? So what happens if it's not single crystal? Well, most materials aren't single crystal. We know that because you don't care about what direction your steel bar is being loaded, because you know it's the same properties in all directions, so something must be different. So the majority of crystalline solids are actually comprised of many single crystals that are agglomerated together, and we call that a polycrystalline material. So here what I'm showing you is a niobium hafnium tungsten plate with an e-beam weld. So here's your length scale of 1 millimeter, and these different colors correspond to different single crystals. So they are presumably they are different orientations, but they also could be different crystal structures depending. Okay, but the bottom line is that every color is an individual crystal. Okay, so what you see is that you have small crystals and large crystals. And each single crystal in the material we're going to call a grain. And the sizes of grains and materials can range from on the order of nanometers all the way up to the order of centimeters. So they can span a dramatic, that would be like a 7 order of magnitude span of size. Okay. Again, going back to our processing of things like steels, a lot of our heat treatments and things are designed to control the size of grains and the regularity of grain sizes. Okay, so in this particular instance, you have large grains and then you have tiny grains, and that's actually not ideal. A lot of times we want to normalize the grain size, and we'll talk about how we do that in steels. The boundary between the individual grains is called a grain boundary. And then how about properties? What do we think about properties in this material? This is kind of a bad example because it's a weld, it kind of ran in a single direction. But if you think about maybe properties in this where all these tiny grains are, what you're going to find is that the properties are typically isotropic, right? So that means that they're the same in all directions. Even though the individual crystals, in any particular color that we would choose there, they're anisotropic. But in aggregate, as we clump them all together and they're all rotated randomly, they typically behave the same in all directions because of all of them clumped together, okay? So, for example, now go back to our iron example. If you remember, we showed one direction along the diagonal giving us, for iron, a modulus of 273 GPa, and then along the 100 direction was 125. But if you measure the modulus of polycrystalline iron, which would kind of be what your iron bar would be, you'll get a modulus of about 210 GPa. Okay? In terms of fabrication, as you might expect, we fabricate single crystals from a variety of nuclei, and as they grow together, then they form at their boundaries, they form grain boundaries, and they give you what you see in this picture, okay? Something like that. So they all grow together. This is the most common way that materials form, but there are ways that we can process these to control how big the grains are, maybe even sometimes the shape of the grains and those kinds of things. We'll talk about those as we move on, but we don't really have all the tools yet to talk about that. We need to talk about things like defects. We need to talk about things like dislocations and whatnot, so that we can kind of properly understand how all of this fits together. Okay, so that's the distinction between single crystal and polycrystal. Now we want to talk in our next lecture about how are we going to take a piece of material and decide what its crystal structure is. How in the world did a map like this ever get generated where we could actually look and say, oh, this location has a different crystal structure than some other location? I want to talk about that. Okay, so hopefully that's straightforward, and we'll slide into that in the next lecture.